Hello, this is Yashvin. In this video, I'll be solving May-June 2017, paper 2 written 29701 chemistry. Starting with question number 1, the composition of atoms and ions can be determined from knowledge of atomic number, nucleon number, and charge. A. Complete the table. So we're supposed to complete this table with the help of the data given. So the first one, we are given with the atomic number. The nucleon number is supposed to be calculated. Nucleon number is basically the number of protons plus the number of neutrons, and that is the mass number over here, which is 6. Number of protons is basically the atomic number, which is 3, and the number of neutron can be calculated by subtracting the number of proton from the relative atomic mass. So 3 minus 6 is 3. In the second case, we are given with the number of electrons, the number of protons, and the number of neutrons. So first off, you can see that the number of electrons and protons is not equal, therefore it is a charge, and since number of protons is greater, that means the particle is a cation. And you can calculate the mass number by adding up the number of protons and neutrons, which would give you 58. And using the periodic table, you would be able to find out that this cation is the iron with a charge of +3 because it has 3 less electrons than protons. So I'll go ahead and write down the nucleon number as 58 and the atomic number as 26. B. Boron occurs naturally as a mixture of two stable isotopes, B10 and B11. The relative isotopic masses and percentage abundances are shown. 1. Define the term relative isotopic mass. So this is mass of an isotope on a scale where carbon-12 has a mass of 12 units. And you just need to write down that definition. Calculate the relative isotopic mass of boron 11. Give your answer to 6 significant figures and show your working. Now here, using the periodic table, you can find out that the atomic mass of boron is 10.8, and then you can use the formula where you have to add sum of all of the products of isotopic mass and its percentage abundance. Divide that by 100 to get the isotopic mass, which in this case we'll be using as 10.8. So I'll go ahead and do that. We're given that the percentage abundance of the second isotope, but not its isotopic mass. So I'll denote that by X over here. Question 2. Nitrogen gas is very unreactive. A. Explain why nitrogen gas is so unreactive. So for it to react, it would have the bonds between nitrogen atoms, which is a triple bond, would have to break down, and because it is not weak, it is quite a strong bond, it would require a very high amount of energy to be broken. That is why it does not very easily react. And the other reason is that it does not have a dipole either, because in reactions usually the dipoles are what cause the reactants to form products. Since nitrogen doesn't have any dipole, that also plays a role in making it unreactive. B. Despite the low reactivity of nitrogen, oxides of nitrogen occur in atmosphere through both natural and man-made processes. 1. Explain why oxides of nitrogen can be made by internal combustion engines. So in internal combustion engines, the temperature is quite high, which provides the energy required to break the strong triple bond in nitrogen and cause its reaction with oxygen. and that is the answer over here. 2. State and explain using a suitable equation how oxides of nitrogen produced by internal combustion engines can be prevented from reaching the atmosphere. We don't want oxides of nitrogen to leave the engines and reach atmosphere, and to ensure that does not happen, cars usually have catalytic converters installed inside them, and they convert nitrogen oxide to nitrogen dioxide while oxidizing carbon monoxide to carbon dioxide. 3. State the role of nitrogen dioxide in the formation of acid rain by oxides of sulfur. Write suitable equations to explain this role. So over here the acid rain is going to be caused by oxides of sulfur, and nitrogen dioxide is going to be playing a role in oxidizing sulfur dioxide to sulfur trioxide, which would then further dissolve in water to form H2SO4 or sulfuric acid. And so nitrogen dioxide acts as an oxidizing agent. 4. Suggest an equation to show how nitrogen dioxide can contribute directly to acid rain. So now we don't want it to act as a catalyst to convert sulfur dioxide and sulfur trioxide, which would have initially caused acid rain, but now we want the oxide itself to contribute to acid rain. That can happen according to the following equation. When nitrogen dioxide reacts with rainwater in the presence of oxygen to form nitric acid. See, explain how the uncontrolled use of nitrite fertilizers on land can lead to a severe reduction in water quality in rivers. So here you're supposed to give a brief summary of eutrophication, and what happens is these nitrite fertilizers are usually soluble in rainwater, and they are washed out of the soil and into water bodies where they cause growth of algae, and that prevents sunlight reaching plants underneath the surface, because the surface is where the algae grows, and when sunlight does not reach plant underneath the surface, they are not able to photosynthesize and produce oxygen. Due to this lack of oxygen, plants and animals in the water bodies usually die. 3. The halogen halides, hydrogen chloride, hydrogen bromide, and hydrogen iodide can undergo thermal decomposition. In a sealed container, an equilibrium is established according to the equation shown, where X can be any of the halogens, chlorine, bromine, or iodine. A. Some bond energies are shown in the table. Use the data to calculate a value for enthalpy change for the thermal decomposition of hydrogen bromide according to the equation shown. What happens in the reaction is that the bond between hydrogen and bromine in this case is broken down, and the bonds between hydrogen atoms and the halogen atoms or bromine atoms form, and that is what you're supposed to use for the calculation part in here. Since bond breaking is endothermic, the first part of the equation is going to be positive, so that will be 2 times 366, because 2 bonds between hydrogen and bromide are going to break down as there are 2 molecules, and then we subtract the bond energies of hydrogen atom and bromine atom, because bond making is exothermic. So you add up those values. B. At a temperature of 700 Kelvin, a sample of hydrogen bromide is approximately 10% decomposed. Changing the temperature affects both the rate of decomposition of hydrogen bromide and the percentage that decomposes. The Boltzmann distribution for a sample of hydrogen bromide at 700 Kelvin is shown. EA represents the activation energy for the reaction. 1. Using the same axis, sketch a second curve to indicate the Boltzmann distribution at a higher temperature. So at a higher temperature, first off, the activation energy would remain the same, but a greater proportion of molecules, reactant particles, would have energy greater than activation energy, or in other words, the area under the graph beyond this label would increase, and for that to happen, the area of the graph to the left side of the label would have to decrease, because total area has to remain the same. So this is how your graph should look like somewhat. It's supposed to start at the origin, because no molecule has zero energy, and the activation energy remains the same. 2. With reference to the curves, state and explain the effect of increasing temperature on the rate of decomposition of hydrogen bromide. So first off, the rate increases because reactant particles have greater kinetic energy, so they move faster and collide faster. And as you can see over here, a greater proportion of molecules has energy greater than activation energy. Earlier, there were only a few molecules, however, now there are more of them with energy greater than activation energy, and because of that they are able to collide with enough energy that leads to a reaction. 3. The decomposition of hydrogen bromide is endothermic. State the effect of increasing temperature on the percentage of hydrogen bromide that decomposes. Use Le Chatelier's principle to explain your answer. Le Chatelier's principle states that when a change is introduced into an equilibrium, the equilibrium changes or shifts its direction to oppose this change. Now, when you increase the temperature, it shifts in a direction which is going to absorb that energy, and that is going to be the reaction which takes in energy or is endothermic. And because of that, when you increase temperature, the decomposition of hydrogen bromide increases. 4. At 700 Kelvin, hydrogen bromide is approximately 10% decomposed, but hydrogen iodide is approximately 20% decomposed. Explain this difference with reference to bond strengths and the factors that affect them. So in decomposition, what happens is the bonds between hydrogen and the halide is broken down, and as the question states, hydrogen bromide and hydrogen iodide, when broken down at the same temperature, do not have equal percentage decomposition, or in other words, hydrogen iodide is broken down faster. And that could mean that the bond between hydrogen and iodine is weaker than the bond between hydrogen and bromine. And in this answer, you're supposed to explain why. So bromine has a smaller atomic size compared to iodine, as a result of which it has fewer shells and therefore less shielding, and in which in turn means the nuclear attraction for the covalent bond pair between hydrogen and bromine is greater when compared to iodine, because it has a larger atomic size, greater shielding effect, and therefore much less nuclear attraction for the electron bond pair, and that is why its bond is much easier to be broken than that of hydrogen bromide. C. At temperatures above 1500 Kelvin, hydrogen chloride will decompose. A sample of 0.3 mole of hydrogen chloride decomposed in a sealed container. The resultant equilibrium mixture was found to contain 1.5 times 10 to the power of -2 mole of chlorine. 1. Calculate the amounts in mole of hydrogen and hydrogen chloride present in equilibrium mixture. I'll start with drawing the ice table, but first I'll write down the equation itself. So we have ICE, the three stages, where I stands for initial molar amounts, C stands for the change in molar amounts, and E stands for the molar amounts of reactants and products present at equilibrium. We're given that we start with a sample of 0.3 mole of hydrogen chloride, so I'll write that down over here and nothing else. So we'd assume that there's 0 mole of hydrogen and chlorine initially, and we're also given that at equilibrium there is 1.5 times 10 to the power of -2 mole of chlorine, and I'll write that piece of information over here. In change, you're supposed to either add or subtract molar amounts. That depends on the side. Since we are starting with the reactant, which is hydrogen chloride, we subtract from the reactant side and add to the product side. As you saw, initially it was 0, and now you have 1.5 times 10 to the power of -2 mole of chlorine. You add the same value to chlorine and also to hydrogen, because they have the same molar value in the equation, as you have 1 mole of hydrogen and 1 mole of chlorine for every 2 moles of hydrogen chloride. So you added those to the product side. Now coming to reactant side, you are going to subtract, because the products formed are going to be using up the reactants that you started with. And now to subtract the value, you're going to multiply 1.5 times 10 to the power of negative 2 with 2 and subtract the answer from 0.3. I don't have much of space around the table, so I'll write that down over here. So subtract from 0.3 the product of twice of 1.5 times 10 to the power of negative 2, because for every 1 mole of hydrogen and chlorine that is broken down, 2 moles of hydrogen chloride are used up, and that gives the answer as 0.27 mole. Now you have the molar amount of hydrogen and hydrogen chloride at equilibrium, so you can write that down. To calculate the mole fraction of each gas in the equilibrium mixture, and to calculate mole fraction, all you're supposed to do is for the compound or the reactant, you're supposed to divide its number of moles. Let's say hydrogen chloride, we divide 0.27 with the total amount of moles present at equilibrium, and to calculate the total amount, you would add up hydrogen and the amount of hydrogen, chlorine, and hydrogen chloride. So that would be 1.5 times 10 to the power of negative 2 times 2 plus 0.27, and that would give the total amount of mole as 0.3. Starting off with hydrogen chloride, we have 0.27 divided by 0.3, and that is equal to 9 over 10. Hydrogen and chlorine are going to be equal because they had equal molar amounts at equilibrium, so that will be 0.015 divided by the total amount, which is 0.3, and that gives the answer as 1 over 20 for both of them. In another experiment, under different conditions, an equilibrium mixture was produced with mole fractions for each species as shown. 1. Write the expression for the equilibrium constant for the decomposition of hydrogen chloride. To calculate that, you need to multiply the partial pressure of hydrogen with partial pressure of chlorine, that is basically the partial pressures of reactants, and divide the value with the partial pressure of hydrogen chloride to the power of 2, because you have 2 moles in the equation. To explain why the total pressure of the system does not need to be known for equilibrium constant to be calculated for this experiment. To calculate the equilibrium constant, what you'd have to do is calculate the mole fraction of each reactant and the product, and then multiply that with the total pressure. So as you can see over here, if you had the total pressure, you would multiply that with the mole fraction of hydrogen, with that of chlorine, and with that of hydrogen chloride. Supposing x is the value of mole fraction of each of the reactants and products, we'd have x times the total pressure, which I'd indicate by P. So that would be hydrogen, this one here would be chlorine, and then we'd have of hydrogen chloride, and since that is squared, you'd have that twice. Now as you can see over here, there is equal amounts of moles in the reactant and the product side, or in the numerator and denominator, so the value of total pressure would cancel out. That is why you don't need the value of total pressure. 3. Calculate the value of equilibrium constant for this experiment. So multiply the values of partial pressures of hydrogen with chlorine, and then divide that by the partial pressure of hydrogen chloride and square that, which gives the answer as 4.649 times 10 to the power of negative 3. For A, the hydrocarbons A, C4H10 and B, C4H8 are both unbranched. A does not decolorize bromine, that is to say, it does not have any double bond, which you can also make out by the molecular formula of A. B decolorizes bromine and shows geometrical isomerism. 1. Draw the skeletal formula of A. So A is just a straight chain hydrocarbon. suggests why unbranched A has a higher boiling point than its branched isomer. Alright, let me give you an example over here. Say this was A that is not branched and this was its branched isomer. The boiling point depends upon the intermolecular forces between these two molecules. For A to boil, the temperature would have to overcome the intermolecular forces or the forces of attraction between these two molecules. Right. So as you can see over here, this unbranched structure provides greater surface area for contact or allows closer packaging, whereas in this case over here, the packaging is not as close. Therefore, the intermolecular forces do not have as much of strength compared to an unbranched structure. And these forces are due to induced dipoles. We can start off by writing that branched isomers have lower contact surface area and therefore they have lower strength of intermolecular forces that are present due to induced dipoles. 3. Give the structural formula of B. So the possible structures of B would mean the double bond could be between the first and second carbon atom or the second and third carbon atoms, but we are given in the question that B shows geometrical isomerism. That means it has to have a double bond between second and third carbon atom to have two different groups of atoms bonded to the two carbon atoms involved in the double bond. And that would mean the structure would be as follows. 4. Explain why B shows geometrical isomerism. Geometrical isomerism is a branch of stereoisomerism which occurs in compound having double bonds between carbon atoms, and the carbon atoms that are involved have two different groups of atoms bonded to them. So you can write it down over here, and the double bond restricts the rotation. 4. Draw the mechanism of reaction of B with bromine. Include all necessary charges, dipoles, lone pairs, and curly arrows. So this is going to be an electrophilic addition reaction because bromine over here acts as an electrophile and the double bond between carbon atoms is broken down. So I'll draw the structure of B. And the bromine from the bromine diatomic molecule, which is closer to the double bond, gets a partial positive charge, and the one further away has a partial negative charge because the electron density in the pi bond between carbon atoms repels electrons from the bromine closer to it away, and that induces a partial positive charge. Now the electrons from the pi bond between carbon atoms are going to be pulled away from this bond to form a bond between carbon atom and the bromine, which has a partial positive charge. So you're going to have to show that by a curly arrow. Now that bromine would gain electrons from carbon atoms, it would no longer need the electrons from the covalent bond between the bond which it has with the second bromine atom, and so it would lose that electron, and that electron along with its own are going to be gained by the second bromine atom. So the structure that follows is one of the carbon atoms bonded to bromine, and the rest of the structure of B follows out. Now that the second carbon in the double bond has lost an electron, it is going to have a charge of +1, and the bromine, which gained an electron, has a charge of -1. And these two charges are going to be attracted together and they form a bond. 6. Explain the origin of the dipole on bromine in this mechanism. So as mentioned earlier, the proximity to high electron density of pi bond between the carbon atoms with double bond causes electrons to be repelled away from bromine, which induces this positive charge. B. The alcohols C and D are isomers of each other with molecular formula C4H10O. Both isomers are branched. When C is heated under reflux with acidified potassium dichromate, no color change is observed. That means C is not oxidized or and therefore it has to be a tertiary alcohol. When D is heated under reflux with acidified potassium dichromate, the color of mixture changes from orange to green, or it is oxidized, and E is produced. E reacts with aqueous sodium carbonate to form carbon dioxide. Now E has to be an acid for it to react with sodium carbonate, and that means if D is oxidized to form E, an acid, D has to be a primary alcohol, since secondary alcohols are oxidized to ketones which cannot be further oxidized, but primary alcohols get oxidized to aldehydes which are then further oxidized to acids, and it is only acids that are able to react with sodium carbonate. So I'll start by identifying C, which is a tertiary alcohol, and that would be 2-methylpropane-2-ol. D is going to be a primary alcohol, but it, as the question mentioned, it is going to be branched. So the branch can be on the second carbon atom, and that would make it 2-methylpropane-1-ol. Let's look at the structure of D. We know that it is going to be a primary alcohol, so it is going to have 2 H's. Now we're left with 3 carbon atoms from the original, from the 4, and we're told that it is a branched structure. That means the last carbon atom has to be a branch on the second carbon atom, because if you drew it on this last carbon over here, it would not be branched, it would be a straight chain alcohol. So I draw it on the second carbon atom, and this would make it 2-methylpropane-1-ol. And this is oxidized to carboxylic acid, and that would be 2-methylpropanoic acid. To write the equation for the reaction between E and aqueous sodium carbonate, so you have C4H8NO2, the formula of compound in the question, which reacts with sodium carbonate, and that is going to be so. React together, we had 2-methylpropanoic acid, assuming this is the acid group over here. It reacts with sodium, so sodium is going to displace this hydrogen atom, and the result is going to be, I'm just going to draw the carbonyl part of the compound, and sodium is going to displace hydrogen. C isomers F and G, C5H10O, both form an orange precipitate when reacted with 2,4-D and pH, meaning F and J have to be either an aldehyde or ketone. F is unbranched and reacts with alkaline aqueous iodine to produce a yellow precipitate, meaning that that means F has carbon bonded to double bonded to oxygen, and it is also bonded to a CH3 group, and then the rest of the structure, which is going to be 3 of the carbon atoms, since this is a straight chain product with no branches, so this will be F. Right. G does not react with alkaline aqueous iodine. It contains a chiral center and produces a sulfur mirror when warmed with Tollens reagent, meaning G is an aldehyde. So we can draw that over here, an aldehyde, and it has a chiral center. It does not react with aqueous alkaline iodine. Let's start by drawing a straight chain for this one. We'd have 5 carbon atoms, but we're given in the question that this is going to be a branched structure. Now we could have drawn that branch over this carbon in here, the second carbon. We could have drawn the branch over this carbon, which would be the third carbon atom, but doing that would not make this compound a chiral product. So I'm going to draw this branch on the second carbon atom instead, and as you can see, this makes the compound a chiral product with the chiral carbon over here in the second position. 1. Name the yellow precipitate formed by the reaction between F and aqueous alkaline iodine. So that is called triiodomethane. to give the structural formula of F and G. So you can just write down these structures over here. For G, since we have a methyl branch over here, I put brackets and then the aldehyde group follows out. 3. Explain the meaning of the term chiral center. The H and I are isomers with molecular formula C2H4O2. The infrared spectra of isomers H and I are shown. 1. Identify the bonds responsible for peaks above 1500 per centimeter in each spectrum. So looking at spectrum H, we can see that there's an absorbance somewhere around 1700 and this value around 300, which is comparatively broad, and therefore when you look at the values given in the data booklet, the bond responsible for this value is going to be the double bond between carbon and oxygen, and this one is a broad sharp absorbance, which could be due to the alcohol group, or more specifically the bond between carbon and OH in the acid part of a compound. And looking at I over here, we similarly have an absorbance around 1700, which is again going to be due to carbon and the double bond between carbon and oxygen. And this absorbance is over here is not as sharp or broad, but is somewhere between 2900 to 3000. And when you look at the values given in the data booklet, the bond between carbon and hydrogen is a possibility over here. So we can write it over here, carbon, oxygen, and the OH, that is basically a part of CO2H in an acid. And similarly we have another carbon oxygen double bond and then a carbon hydrogen bond. Name H and I. So the formula is C2H4O2. Assuming that H is an acid, I'd first draw the acid part, which is CO2H, and then of course the remaining carbon and hydrogen atoms. And in I, we have the double bond between carbon and oxygen. Now we don't have the absorbance for an alcohol group, so we'd assume that this is an ester, and that gives the only possible position for the second oxygen atoms in the molecular formula, and this is C, by the way. The rest of the hydrogen atoms as drawn in here. So that makes H ethanoic acid and I methyl methanoate.